Look up at the sky right now, that bright, warm star that's been shining down on us every single day of our lives, the star that made everything on Earth possible, is actually a ticking time bomb, and we know exactly when it's going to go off. In about 5 billion years, our sun will transform into something so massive, so incomprehensibly large, that it will quite literally swallow the Earth whole. This isn't science fiction. This isn't speculation, this is the inevitable fate written in the laws of physics, and today we're going to explore every terrifying and fascinating detail of how our star will die, and take us with it. Right now, at this very moment, the sun is engaging in the most spectacular act of cosmic balance ever conceived. Deep in its core, 400 million tons of hydrogen are being converted into helium every single second through nuclear fusion. Think about that number, 400 million tons, every single second. This process releases an amount of energy so staggering that if we could harness just 1 second of the sun's output, we could power all of human civilization for hundreds of thousands of years. The sun has been doing this for 4.5 billion years, and it will continue for another 5 billion more, but nothing lasts forever, not even stars. The sun is what astronomers call a main sequence star, specifically a G-type yellow dwarf. Despite the name dwarf, our sun is actually bigger than about 85% of all stars in our galaxy. It's a medium-sized powerhouse that sits in a sweet spot of stellar evolution. It's not so massive that it burns through its fuel in just a few million years like the blue giants. And it's not so small that it will smolder for trillions of years like the red dwarfs. The sun is just right, which is exactly why we're here to talk about it. Life needed that Goldilocks star, that perfect middle ground of stability and energy output, to evolve over billions of years. But that stability comes with an expiration date. Right now, the sun is in its comfortable middle age, about halfway through its main sequence lifetime. The core temperature hovers around 15 million degrees Celsius, hot enough to fuse hydrogen into helium through a process called the proton-proton chain reaction. For hydrogen nuclei combine to form one helium nucleus, and in that process, a tiny amount of mass is converted directly into energy according to Einstein's famous equation, E equals mc squared. That tiny bit of mass, multiplied by the speed of light squared, gives you an almost incomprehensible amount of energy. This is what makes the sun shine, this is what warms your face on a summer day, this is what drove photosynthesis in the first plants and what powers the weather systems and ocean currents of our planet. The radiation pressure from all this fusion pushes outward, while gravity pulls inward, and the two forces are in perfect equilibrium. The sun is neither collapsing nor exploding, it's balanced. But here's the thing about burning fuel, eventually you run out. The core of the sun is slowly but surely accumulating helium ash. Think of it like a campfire that burns wood and creates ash. The wood burns great, gives off heat and light, but the ash just sits there. Helium in the sun's core is like that ash. At the current temperature and pressure, helium can't fuse, it just accumulates, getting denser and denser as more hydrogen gets converted. As the helium builds up in the core, something interesting starts to happen. The hydrogen fusion gets pushed into a shell around the inert helium core. The sun begins to slowly, almost imperceptibly, get brighter. This has been happening throughout Earth's history. When life first appeared on our planet about 3.5 billion years ago, the sun was only about 70% as bright as it is today. That's right. The sun has gotten 30% brighter over the course of Earth's history. This is called the faint young sun paradox, and it's one of the fascinating puzzles in planetary science, because you'd think a dimmer sun would have meant a frozen Earth, yet we know liquid water existed. The answer probably lies in a much thicker greenhouse atmosphere back then, with more carbon dioxide keeping the planet warm. But we're getting ahead of ourselves. Let's fast forward to the real drama. 5 billion years from now, give or take a few 100 million years, the hydrogen in the sun's core will finally, completely run out. At this point, the core is almost entirely helium, compressed to incredible densities by the weight of all the material above it. But remember, helium can't fuse at these temperatures and pressures. The core becomes inert, dead, a stellar corpse at the heart of a still living star. When the fusion in the core stops, there's nothing to produce the radiation pressure that holds the star up against gravity, and gravity doesn't wait. The core begins to contract. As it contracts, it heats up, because when you compress a gas, it gets hotter. This is just thermodynamics. This heating affects the hydrogen shell around the core, making it hot enough to fuse hydrogen at an even faster rate than the core ever did. Here's where things get weird. You'd think running out of fuel would make the star dimmer, right? Wrong, the star gets brighter, much brighter. The increased fusion in the hydrogen shell pumps more energy into the outer layers of the sun than ever before. All this extra energy pushes those outer layers outward. The sun begins to expand, slowly at first, almost imperceptibly, but then faster and faster. The sun transitions from a main sequence star to a subgiant, and eventually to a red giant. The term giant doesn't do it justice. We're talking about a star that will expand to perhaps 100 times its current diameter or more. Right now, the sun is about 1.4 million kilometers across. As a red giant, it could be 140 million kilometers across or even larger. Let's put that in perspective. The Earth orbits at a distance of about 150 million kilometers from the sun. That's one astronomical unit, the fundamental measuring stick of our solar system. When the sun becomes a red giant, its outer atmosphere could reach as far as Earth's current orbit, or even beyond. The sun will literally fill the sky. Imagine that, instead of that familiar disk we see every day. The sun would stretch from horizon to horizon, a roiling, churning sea of plasma that dominates everything. But the expansion doesn't happen overnight. This is a process that takes millions of years. The sun will spend about 1 billion years as a subgiant, slowly swelling and brightening. During this time, life on Earth, if any still exists, will face increasingly hostile conditions. The temperature will rise, the oceans will begin to evaporate, the water vapor will create a runaway greenhouse effect. Similar to what happened on Venus billions of years ago. Venus, our sister planet, probably had oceans once. Then the sun got brighter, the oceans evaporated, and the planet became the hellish, acid rain-soaked pressure cooker we see today, with surface temperatures hot enough to melt lead. Earth will follow the same path. Long before the sun physically swallows our planet, the biosphere will be sterilized, every living thing will die, the oceans will boil away into space, the atmosphere will be stripped off by the solar wind, which will grow stronger and more violent as the sun ages. The surface of the Earth will be baked and blasted until nothing recognizable remains. It's a slow apocalypse, unfolding over millions of years, but utterly inevitable. Of course, humans won't be around to see it. If our species survives for even another 1,000,000 years, which is far from guaranteed given our track record, we'll either have left Earth entirely or evolved into something so different we wouldn't recognize ourselves. 1,000,000 years is a long time in human terms. Modern humans have only existed for about 300,000 years. Agriculture is only 12,000 years old. Industrial civilization is barely 300 years old. Imagining what humanity, or its descendants, will be like in millions of years is nearly impossible. We'll either be gone, extinct like 99% of all species that have ever lived, or we'll have become something new, spread among the stars, looking back at Earth as a distant memory of our species' childhood. But let's return to the sun. As it swells into a red giant, the surface temperature actually decreases. This might seem counterintuitive. The star is getting bigger and brighter, but cooler on the surface. Yes, The enormous expansion spreads the same amount of energy over a much larger area. The surface temperature drops from about 5,500 degrees Celsius to maybe 3,000 degrees. This is why it's called a red giant. Cooler stars appear red, hotter stars appear blue. Our yellow sun becomes a red giant. But don't let the cooler surface fool you. The total energy output, the luminosity, increases dramatically. The sun will be thousands of times brighter than it is today. This increased luminosity comes from the furious fusion in the hydrogen shell around the contracting core. The shell fusion is actually more efficient, more productive, than the core fusion ever was, because the material is denser and hotter. Now, while all this is happening in the outer layers, the core continues its relentless contraction. Remember, the core is inert helium, not fusing, just compressing under its own weight. It gets hotter and hotter and denser, the material becomes degenerate, a strange state of matter where quantum mechanical effects dominate. In degenerate matter, electrons are packed so closely together that the Pauli exclusion principle, which says no two electrons can occupy the same quantum state, provides a pressure that resists further compression. This is called electron degeneracy pressure, and it's not like normal gas pressure. It doesn't depend on temperature, it's a purely quantum effect. The core keeps contracting and heating until, at about 100 million degrees Celsius, something magical happens. Helium begins to fuse. 3 helium nuclei combine to form carbon through a process called the triple alpha process. It's called this because helium nuclei are also called alpha particles, and you need 3 of them. This reaction is much more temperature sensitive than hydrogen fusion. A small increase in temperature leads to a huge increase in fusion rate. In a normal star, one with a non-degenerate core, this would be fine. The increased fusion would heat the core would expand, the temperature would drop a bit, and equilibrium would be restored. But our sun's core is degenerate, temperature and pressure are decoupled. When the helium fusion starts, the temperature skyrockets, but the core doesn't expand because the degeneracy pressure doesn't care about temperature. More heat means more fusion, means more heat, means more fusion. It's a runaway reaction. This is called the helium flash. Within seconds, the core produces as much energy as the entire galaxy. But here's the thing, almost none of that energy escapes. The energy is absorbed by the degenerate matter itself, heating it so much that it lifts the degeneracy. The core is no longer degenerate, it becomes a normal gas again, and it expands, bringing the runaway fusion under control. The entire event happens deep inside the star, invisible from the outside. An external observer would see nothing, but inside, the star has fundamentally transformed. The helium flash marks the transition from the red giant branch to the horizontal branch for stars like the Sun. After the helium flash, the Sun settles into a new equilibrium. It now has helium fusing in the core and hydrogen fusing in a shell around that core. This is a double burning phase. The Sun is now smaller and less luminous than it was at the peak of the red giant phase, but still much larger and brighter than it is today. This phase lasts about 100 million years, a relatively brief moment in stellar terms. During this time, the Sun is fusing helium into carbon and oxygen in its core. Eventually, the helium in the core runs out, and we're back to the same situation as before, an inert core, now made of carbon and oxygen, surrounded by burning shells. But the Sun isn't massive enough to fuse carbon. Stars need to be at least 8 times the mass of the Sun to ignite carbon fusion. Our Sun will never reach those temperatures and pressures. The carbon-oxygen core is the end of the line. What happens next is one of the most beautiful processes in all of astronomy. The star enters the asymptotic giant branch, or AGB phase. It swells up again, even larger than before, becoming a bloated, unstable red supergiant. The fusion shells are thin and unstable, leading to thermal pulses where the helium shell periodically ignites explosively, causing the star to brighten and dim. These pulses happen every 10,000 to 100,000 years and can increase the star's luminosity by factors of 10 or more. During the AGB phase, the Sun will lose mass at a prodigious rate. The outer layers are so loosely bound that even the weak stellar wind can carry them away. The Sun will shed perhaps half its mass over a few 100,000 years. This material, enriched with carbon, oxygen, and other elements synthesized in the star, will be blown into space, creating a vast, expanding shell of gas and dust. Eventually, the envelope is completely lost, exposing the hot core. This core, now about the size of Earth but with about half the Sun's original mass, is incredibly hot, perhaps 100,000 degrees at the surface. The intense ultraviolet radiation from this tiny, hot core ionizes the surrounding gas, making it glow. This is what we call a planetary nebula, one of the most stunning sights in the universe. Despite the name, planetary nebulae have nothing to do with planets. Early astronomers with primitive telescopes thought they looked like planets, round and disc-like, so the name stuck. Planetary nebulae come in an astonishing variety of shapes and forms. Some are perfect spheres, others are bipolar with two lobes, some have intricate, almost fractal patterns. The shapes are determined by the mass loss history of the star, magnetic fields, and whether the star had a companion. They glow in brilliant colors, reds from hydrogen, greens from oxygen, blues from helium. They last for only tens of thousands of years before fading away, the gas dispersing into the interstellar medium. And at the center of the planetary nebula sits the core. This core is no longer producing energy through fusion, it's just sitting there, radiating away its stored heat. This is a white dwarf, the final fate of stars like our Sun. White dwarfs are bizarre objects. They're about the size of Earth but contain half a solar mass or more. A teaspoon of white dwarf material would weigh as much as an elephant. The matter is supported entirely by electron degeneracy pressure. There's no fusion, no chemical reactions, nothing. It's just hot, dense, inert matter slowly cooling off. White dwarfs start out incredibly hot, but over billions of years, they cool and dim. They transition from white to yellow to red and eventually, after an incomprehensible length of time longer than the current age of the universe, they would theoretically become black dwarfs, completely cold and dark. But the universe is only about 14 billion years old, not nearly old enough for any white dwarf to have cooled to this point. Every white dwarf that has ever formed is still glowing. The Sun's white dwarf remnant will continue to exist for trillions of years, a cosmic ember slowly fading in the darkness. It will be a monument to what once was, a stellar graveyard marker. And what of the planets? Mercury, the closest planet to the Sun, will almost certainly be consumed during the red giant phase. There's very little doubt about this. The Sun's outer atmosphere will reach well beyond Mercury's orbit. Venus is also doomed, though there's slightly more uncertainty here. Some models suggest Venus might just barely survive, pushed into a wider orbit by the mass loss from the Sun, but most predict it too will be swallowed. And Earth? This is where it gets contentious. The fate of Earth during the Sun's red giant phase has been debated for decades. Early models suggested Earth would definitely be consumed, but more sophisticated models that account for mass loss from the Sun paint a more nuanced picture. As the Sun loses mass, its gravitational pull weakens. The planets, including Earth, will spiral outward into larger orbits. The question is whether Earth spirals outward fast enough to escape the expanding Sun. Some models say yes, Earth will survive. Pushed just beyond the Sun's maximum radius, baked and lifeless but technically intact. Other models say no. Tidal interactions between the Sun's outer atmosphere and Earth will cause drag, making Earth spiral inward even as the orbit nominally expands outward. ultimately leading to its consumption. The uncertainty comes from imprecise knowledge of the sun's exact maximum radius, the timing of mass loss, and the strength of tidal effects. But let's be clear about one thing: even if Earth physically survives, it will be utterly destroyed as a habitable world long before the sun becomes a red giant. By the time the sun swells to its maximum size, Earth will have been a scorched, airless rock for hundreds of millions of years. Whether the charred husk of our planet is swallowed by the sun or is left orbiting a white dwarf is almost academic. Either way, it's gone in any meaningful sense. Mars, the outer asteroid belt, and the outer planets will survive the red giant phase more or less intact, though they'll experience dramatic changes. The increased solar luminosity will warm these worlds significantly, for a brief period. In cosmic terms, places like Europa or Enceladus, moons that currently harbor subsurface oceans beneath thick ice shells, might have liquid water on their surfaces. They could become temporarily habitable. Then, as the sun sheds its outer layers and becomes a white dwarf, they'll freeze solid again, harder than ever before. The story of the sun's death is also the story of nucleosynthesis, the creation of elements. When the universe began in the Big Bang, only hydrogen, helium, and tiny traces of lithium were created. Everything else, every atom of carbon in your body, every atom of oxygen you breathe, every atom of iron in your blood, was created inside stars. Stars are element factories. The sun has been converting hydrogen into helium for billions of years. When it becomes a red giant, it will fuse helium into carbon and oxygen. More massive stars go further, creating neon, magnesium, silicon, all the way up to iron. When massive stars explode as supernovae, the tremendous energies involved create elements heavier than iron, things like gold, platinum, uranium. These explosions seed the galaxy with heavy elements. Over time, the interstellar medium becomes enriched with metals. In astronomical terms, metals means anything heavier than helium. New stars form from this enriched material, and planets form around those stars. Rocky planets like Earth can only exist because previous generations of stars lived and died, creating and dispersing the heavy elements. The Sun is a third-generation star, maybe fourth. It formed from a cloud of gas and dust that already contained heavy elements from previous stars. This is why we exist. The atoms in our bodies are stardust. Literally, we are the universe contemplating itself. The death of stars is as essential to the existence of life as their birth. The Sun will end its life by contributing its own enriched material to the next generation of stars, the carbon and oxygen in its core, blown into space by the planetary nebula, will become part of new molecular clouds, new stars, new planets, perhaps new life. This cycle of stellar birth and death has been going on for most of the universe's history. The first stars, called population 3 stars, formed a few 100 million years after the Big Bang from pristine hydrogen and helium. They were probably extremely massive, hundreds of times the mass of the Sun, burning bright and dying young in spectacular supernovae. Their explosions enriched the cosmos with the first heavy elements, allowing the next generation of stars to form. This process has been repeating for over 13 billion years. Our galaxy, the Milky Way, contains hundreds of billions of stars, each at different stages of their lives. Some are just being born in stellar nurseries like the Orion Nebula, clouds of gas and dust collapsing under gravity, fragmenting into hundreds or thousands of protostars. Others are in their prime, stable main sequence stars like the Sun, fusing hydrogen in their cores. Still others are dying, red giants and supergiants. Planetary nebulae, white dwarfs, neutron stars, black holes. The galaxy is a vast ecosystem of stars at every stage of evolution. And it's not just our galaxy. There are at least 2 trillion galaxies in the observable universe. each with billions or even trillions of stars. The number of stars in the universe is so large it's almost meaningless to human comprehension, more stars than grains of sand on all the beaches on Earth, and every single one of those stars has a life cycle, a story of birth, life, and death. Stars like the Sun will become white dwarfs, more massive stars will explode as supernovae, leaving behind neutron stars or black holes. The most massive stars will collapse directly into black holes without even exploding. The Sun's fate as a white dwarf is actually one of the more peaceful endings a star can have, no violent explosion, just a slow, graceful shedding of its outer layers and a long, slow fade into darkness. But even this peaceful death is unimaginably violent and destructive by human standards. The inner solar system will be obliterated. Any remnant of human civilization that might still exist on Earth, or Mars, or the asteroid belt will be vaporized. All traces of our existence will be erased. Unless, of course, we leave, and this is where the story becomes less about astrophysics and more about philosophy and futurism. 5 billion years is an incomprehensible length of time. For comparison, the Earth itself is only 4.5 billion years old. Life has existed for 3.5 billion years. Complex multicellular life has only existed for about 600 million years. Modern humans have existed for maybe 300,000 years. Civilization is 10,000 years old. 5 billion years from now is as far in the future as the formation of the Earth is in the past. What could happen in 5 billion years? If humans or our descendants survive, we will have had time to colonize not just the solar system, but potentially the entire galaxy. With even relatively slow spacecraft traveling at a fraction of the speed of light, you could colonize the galaxy in a few tens of millions of years. We have 5 billion years. We could colonize millions of galaxies if we wanted to. The death of the Sun would be a minor local event. A star in one remote corner of one average galaxy ending its life like billions of others do every day. But maybe we don't leave, maybe we go extinct long before the Sun becomes a threat. We've only had industrial technology for about 200 years, and we've already created the means to destroy ourselves many times over, through nuclear war, engineered pandemics, environmental collapse, or AI gone wrong. There's a concept in astrobiology called the Great Filter. The idea that there's some stage in the development of intelligent life that is extremely difficult to pass. Maybe it's the origin of life itself, maybe it's the development of multicellular organisms, maybe it's the development of intelligence, or maybe it's the stage we're at right now, a technological civilization that has developed the power to destroy itself before developing the wisdom to survive. We look out into the universe and see billions of potentially habitable planets, yet we've found no evidence of other civilizations. This is the Fermi paradox. Where is everybody? Maybe the answer is grim. Maybe most civilizations destroy themselves shortly after developing technology. Maybe we're looking at our own future, or maybe intelligence is just incredibly rare, and we happen to be among the first. Maybe in a billion years, the galaxy will be teeming with our descendants, and the silence we hear now is just because we're early to the party. Regardless of what happens to humanity, the Sun will follow its programmed course. The laws of physics don't care about our hopes, dreams, or survival. The Sun will become a red giant. It will shed its outer layers, it will become a white dwarf. This will happen with the inevitability of mathematics. We can predict it with confidence not because we've watched the Sun do it before, but because we've watched countless other stars do it. We've observed stars at every stage of this process. We've seen young stars, middle-aged stars, red giants, planetary nebulae, white dwarfs. We've pieced together the entire story by looking at different stars at different stages, like watching a film by looking at individual frames scattered randomly on a table. The Sun is currently about 4.6 billion years old. it has perhaps 5 to 5.5 billion years left in its main sequence phase, then a billion years as a subgiant and red giant, with about 100 million years of helium burning, then a few 100,000 years as an AGB star, shedding its envelope, then it's a white dwarf for the rest of eternity, or until the heat death of the universe. Whichever comes first, the process of stellar evolution isn't just theory, we can see it happening in real time, or at least on astronomical timescales. Betelgeuse, the red supergiant in the constellation Orion, is a star in its death throes right now. It's already in the late stages of fusion, burning heavier and heavier elements in its core. When it exhausts its fuel, probably sometime in the next 100,000 years, maybe tomorrow, maybe in 10,000 years, we don't know exactly, it will explode as a supernova. The explosion will be visible from Earth in broad daylight. Brighter than the full moon, it will be one of the most spectacular astronomical events in human history, and then it will fade, leaving behind either a neutron star or a black hole. Betelgeuse is much more massive than the Sun, maybe 15 to 20 times as massive, so its fate is different, but the principle is the same. Stars fuse lighter elements into heavier ones until they can't anymore, and then they die. The Sun will never fuse anything heavier than helium because it's simply not massive enough to create the necessary temperatures and pressures. Carbon fusion requires temperatures of about 600 million degrees. The Sun's core will never get that hot. Stars need to be at least 8 solar masses to fuse carbon. Below that threshold, you end up with a white dwarf. Above it, you end up with a supernova. This mass threshold is one of the most important numbers in astrophysics. It determines the fate of every star in the universe. It's called the Chandrasekhar limit, named after the Indian astrophysicist Subrahmanyan Chandrasekhar, who calculated it in the 1930s. The limit is about 1.4 solar masses, and it represents the maximum mass a white dwarf can have. If you try to pack more mass than that into a white dwarf, the electron degeneracy pressure can't hold it up anymore, and the star collapses further. What happens next depends on how the mass was added. If you have a white dwarf in a binary system and it's slowly accumulating mass from a companion star, when it crosses the Chandrasekhar limit, the carbon and oxygen in the core suddenly ignite all at once in a runaway fusion reaction. The entire star explodes, nothing is left behind. This is called a type Ia supernova. And these explosions are so consistent in their brightness that we use them as standard candles to measure distances across the universe. In fact, observations of type Ia supernovae in distant galaxies in the late 1990s led to the discovery that the expansion of the universe is accelerating, driven by something we call dark energy. This discovery won the Nobel Prize in 2011. If instead the mass is added rapidly, like if two white dwarfs collide and merge, or if a massive star's core collapses, you don't get a thermonuclear explosion. Instead, you get something even more extreme. The electrons are forced to combine with protons to form neutrons. The entire core becomes a giant atomic nucleus made of neutrons packed together. This is a neutron star. An object so dense that a teaspoon of neutron star material would weigh 1 billion tons. Neutron stars are held up by neutron degeneracy pressure, similar to electron degeneracy pressure but operating on neutrons instead. But there's a limit to that too, called the Tolman-Oppenheimer-Fokoff limit. If the core is more massive than about 2 to 3 solar masses, even neutron degeneracy pressure can't hold it up. Nothing can. The core collapses all the way down to a gravitational singularity, a point of infinite density where the laws of physics as we understand them break down. A black hole forms, a region of spacetime where gravity is so strong that nothing, not even light, can escape. The Sun will never experience any of this. It will never cross the Chandrasekhar limit. Its white dwarf remnant will have a mass of perhaps half a solar mass. Well below the threshold, it will simply sit there, cooling off for eternity. This is simultaneously comforting and somewhat anticlimactic. The sun won't go out with a bang, it goes out with a wheeze, a slow exhalation of gas and dust, and then silence. But let's talk more about what the red giant phase will actually look like from an observer's perspective. If any observers still exist, imagine you're standing on Mars, somehow protected from the harsh environment, watching the sun transform over millions of years. At first, the changes are subtle. The sun appears slightly brighter, slightly larger in the sky. Over generations, the difference becomes more pronounced. The sun is noticeably bigger, noticeably brighter. The ice caps on Mars begin to melt for the first time in billions of years. The atmosphere thickens as frozen carbon dioxide sublimates, the temperature rises. Centuries pass, millennia, the sun continues to swell. It's no longer a point of light but a visible disk that grows larger year by year. The Martian sky, normally a butterscotch color from the dust, begins to take on strange hues as the sun's spectrum shifts toward the red. The sun is now so bright that even on Mars, protected by greater distance, the temperature is rising to uncomfortable levels. Any water that existed underground is now boiling to the surface. The planet is transforming. More time passes, the sun now dominates the sky. It's enormous, spanning dozens of degrees across. From Mars, you can see details on its surface, vast convection cells, bright and dark regions, massive prominences arcing into space. The sun has become a red giant, and even from Mars's greater distance, it's a terrifying sight. The temperature on Mars is now hundreds of degrees. The surface glows with its own heat. Any complex molecules, any organic chemistry, has been destroyed. But Mars is far enough away that it survives. Earth does not. From Mars, you could watch Earth die. If you had a powerful enough telescope and could somehow observe through the sun's glare, you would see Earth spiral slowly inward, its orbit decaying as it interacts with the tenuous outer atmosphere of the sun. The planet would glow white-hot from the friction, leaving a trail of vaporized rock behind it, and then, one day, it would slip beneath the visible surface of the sun and disappear. Forever, vaporized in an instant. The outer planets fare better, in relative terms. Jupiter, Saturn, Uranus, Neptune are far enough away that they're never in danger of being swallowed, but they experience dramatic changes too. The intense radiation from the red giant sun heats their atmospheres, causing them to expand. Jupiter might lose a significant fraction of its atmospheric mass. The planet's famous bands and storms would become even more chaotic and violent. The moons of Jupiter, especially the Galilean moons, would undergo incredible transformations. Europa, currently covered in a thick shell of ice over a subsurface ocean, would see that ice completely melt. For perhaps a few million years, Europa would have a liquid water ocean exposed to space. Could life emerge in such a short time? Probably not. Evolution takes time, and a few million years isn't nearly enough to go from chemistry to biology, at least not as far as we understand it, but it's a fascinating thought experiment. The same would happen to Enceladus around Saturn, and other icy moons throughout the outer solar system. Then, as the sun sheds its outer layers and contracts into a white dwarf, the luminosity drops precipitously, the temperature throughout the solar system plummets, Jupiter and its moons freeze solid, harder and colder than ever before. The brief warm period is over. The white dwarf sun, though incredibly hot at its surface, is so small that it emits relatively little total energy. The solar system becomes a dark, cold place. The white dwarf sun would be visible from the outer planets, a brilliant point of intense white or blue light, but it wouldn't provide significant warmth. The planets would be lit by starlight, not sunlight. This is the final configuration of the solar system, a white dwarf star surrounded by a debris field of whatever planet survived, probably Mars, the asteroid belt, Jupiter, Saturn, Uranus, Neptune, and their moons, plus the Kuiper belt and Oort cloud, Earth is gone, either swallowed by the Sun or vaporized in its outer atmosphere. Venus and Mercury are definitely gone. The inner solar system is empty. Any asteroids that were in the asteroid belt might have been perturbed into new orbits by the changing mass distribution of the Sun. Some might have been flung out of the solar system entirely, others might have crashed into the surviving planets. It's a solar system that would be barely recognizable to us, cold, dark, and dead. The white dwarf would shine for trillions of years, slowly fading, moving through the spectrum from white to yellow to red to infrared, eventually becoming a black dwarf, a completely cold, dark stellar remnant. But as we mentioned, the universe isn't old enough for any black dwarfs to exist yet. The oldest white dwarfs, formed in the first billion years after the Big Bang, are still glowing faintly. They won't become black dwarfs for another 10 trillion years or more. 10 trillion years is an almost incomprehensible timescale. For comparison, the universe is currently 14 billion years old. 10 trillion years is more than 700 times the current age of the universe. By that time, if current cosmological models are correct, the universe will have changed beyond recognition. Star formation will have essentially ceased because most of the hydrogen will have been locked up in stars, white dwarfs, neutron stars, and black holes. The galaxies will be dark places, lit only by the fading light of the longest-lived red dwarf stars and the occasional supernova from late-forming massive stars. Galaxies themselves will have different configurations. The Milky Way and Andromeda, our nearest large galactic neighbor, are currently on a collision course. In about 4 billion years, around the same time the Sun is beginning its transformation into a red giant, these two galaxies will collide. But don't picture stars smashing into each other like billiard balls. Galaxies are mostly empty space. The distances between stars are so vast that even when two galaxies merge, direct collisions between stars are incredibly rare. What does happen is that the gravitational interactions between the two galaxies distort them, triggering waves of star formation as gas clouds collide and collapse. The galactic centers, each containing a supermassive black hole, will eventually merge into a single, even more massive black hole. The result will be a new, larger elliptical galaxy, sometimes called Milkomeda or Milkdromeda. Our solar system will be part of this new galaxy, flung into a new orbit, possibly ejected into the intergalactic void, or perhaps drawn toward the new galactic center. So the Sun doesn't die in isolation, it dies as part of a much larger cosmic drama, the merger of two galaxies. The Sun will be becoming a red giant right around the time the Milky Way and Andromeda are in the throes of their collision. The sky will be spectacular, if anyone is around to see it. Andromeda, currently a faint smudge visible to the naked eye on dark nights, will grow larger and larger, eventually filling a huge portion of the sky. New stars will be forming at a prodigious rate in the collision zones, lighting up the night sky with brilliant blue light from massive young stars. And then, over hundreds of millions of years, the two galaxies will merge fully, settling into a new configuration. The era of spiral galaxies will be over. Milkomeda will be an elliptical galaxy, a ball of stars with no clear structure, no spiral arms. Star formation will eventually slow and stop as the available gas is exhausted. The galaxy will age, its stars evolving and dying one by one. On even longer timescales, trillions of years from now, galaxies themselves will begin to evaporate. Stars occasionally pass close to each other, and these gravitational interactions can give one star enough energy to escape the galaxy entirely. Over incredibly long periods, galaxies will slowly lose their stars to the intergalactic void. Eventually, only the most tightly bound stars, those closest to the central supermassive black hole, will remain. Everything else will have wandered off into The darkness. The universe will become a sparse, lonely place. Stars will be separated by unimaginable distances, isolated in the void. Most of the matter in the universe will be locked up in degenerate stellar remnants, white dwarfs, neutron stars, and black holes. The last red dwarf stars, the smallest and longest-lived stars, will finally exhaust their fuel and fade away after 10 trillion years or more. After that, the only sources of light will be occasional supernovae from white dwarf collisions and the Hawking radiation from evaporating black holes. Yes, even black holes evaporate. Stephen Hawking discovered in the 1970s that black holes aren't completely black. They emit radiation due to quantum effects at the event horizon. The smaller the black hole, the faster it evaporates. Stellar mass black holes will take something like 10 to the 67 years to evaporate. Supermassive black holes, like the ones at the centers of galaxies, will take even longer, 10 to the 100 years or more. These numbers are so large they're almost meaningless, but the point is that given enough time, even black holes die. In the far, far future, after all the black holes have evaporated, the universe will enter what's called the dark era. No stars, no black holes, just a thin soup of elementary particles, photons, neutrinos, and electrons, all moving away from each other. As the universe continues to expand, the temperature will be a tiny fraction of a degree above absolute zero. Nothing will happen, nothing can happen. There's no free energy left to drive any processes. The universe will have reached heat death. Maximum entropy, a state of perfect equilibrium where nothing changes anymore. Unless, of course, our understanding of physics is wrong. There are speculative ideas about how the universe might end differently. Maybe the expansion will reverse, and everything will collapse back into a big crunch. Maybe the accelerating expansion will tear everything apart in a big rip. Maybe protons themselves decay, and matter as we know it will cease to exist on timescales of 10 to the 34 years or so. Maybe quantum fluctuations will eventually produce new big bangs, baby. Universes budding off from our own, we don't know. The far future is deeply uncertain. But the near future, the next few billion years, we understand pretty well. The sun will become a red giant, that's certain. The physics is well understood, and we've observed the process in countless other stars. We know what's going to happen. The only uncertainties are minor details, like the exact timing, the exact maximum radius, whether Earth survives or not. The broad strokes are clear. And here's something mind-blowing to consider. The sun's transformation into a red giant isn't unique. It's happening to stars all over the universe, all the time, right now, at this very moment. Somewhere in the universe, a star is running out of hydrogen in its core. Somewhere, a star is igniting helium in a helium flash. Somewhere, a star is pulsing on the asymptotic giant branch, shedding its outer layers. Somewhere, a planetary nebula is forming. Somewhere, a white dwarf is cooling. The death of the sun is a cosmic commonplace, an event that happens billions of times in every galaxy. From a galactic perspective, the death of a single star is utterly insignificant. The galaxy doesn't care, the universe doesn't care. Stars are born, live, and die with the regularity of clockwork. The Milky Way contains somewhere between 200 and 400 billion stars. Every year, about 7 new stars are born in our galaxy. And about 7 old stars die. The cycle continues, has continued for billions of years, will continue for billions more. But from a human perspective, from the perspective of life on Earth, the death of the sun is the ultimate deadline. It's the final exam we can't postpone. If we want to survive as a species, we need to leave Earth eventually, not tomorrow, not in 1,000 years, probably not even in 1,000,000 years. We have time, but the clock is ticking. 5 billion years might sound like forever, but it's not. It's a finite amount of time. And that time is passing. The question is whether we'll rise to the challenge, will humanity, or whatever we evolve into, become a spacefaring civilization? Will we spread to the stars, ensuring our survival beyond the death of our home star? Or will we go extinct long before that becomes necessary, another failed experiment in the universe's ongoing attempt to produce complexity and intelligence? The history of life on Earth suggests that extinction is the norm. 99.9% of all species that have ever lived are now extinct. The average lifespan of a mammalian species is about 1 million years. Modern humans have existed for maybe 300,000 years, so if we're average, we have about 700,000 years left. But of course, we're not average, we have technology. We have the ability to shape our environment, to cure diseases, to potentially even modify our own biology. We might be able to extend our survival well beyond what natural selection alone would allow. But technology is a double-edged sword. It gives us the power to survive, but also the power to destroy ourselves. Nuclear weapons, engineered pandemics, climate change, artificial intelligence, nanotechnology gone wrong. There are so many ways we could end our own story prematurely, and unlike natural disasters, these are threats of our own making. We have met the enemy, and he is us. If we do survive, if we do become a spacefaring civilization, what might that look like? There are different approaches to interstellar colonization. One is the Generation Ship, a massive spacecraft that travels for hundreds or thousands of years between stars, with multiple generations of people living and dying aboard. Another is suspended animation, freezing colonists for the journey and waking them upon arrival. Another is to not send humans at all, but to send AI and robots that can build the infrastructure, and then either create humans from stored genetic material or wait for humans to arrive later. Or maybe we don't send biological humans at all. Maybe by the time we're ready to colonize the stars, we'll have uploaded our consciousnesses into computers, becoming digital beings that don't need air, food, water, or protection from radiation. Digital beings could travel at the speed of light as pure information, beamed from star to star, reconstructed in computers at the destination. The journey from Earth to Alpha Centauri, our nearest stellar neighbor at about 4 light-years away, would take just 4 years from Earth's perspective, and essentially no subjective time for the digital traveler, who could simply be paused during transit. These ideas sound like science fiction, and they are, but they're not impossible. They don't violate any known laws of physics. They're just engineering problems, albeit incredibly difficult ones. If we survive long enough, if we develop the technology, there's no reason in principle we couldn't colonize the galaxy, and if we can colonize our galaxy, other civilizations in other galaxies could do the same. The universe could eventually be full of intelligence, full of life, all descended from those rare planets where life happened to emerge and evolve to the point of developing technology. Or maybe we're alone, maybe life is common, but intelligence is incredibly rare. Maybe the universe is full of bacteria and algae and maybe even complex multicellular organisms, but we're the only civilization. This is a sobering thought. It would mean we have a responsibility not just to ourselves, but to the concept of intelligence itself. If we go extinct, there might not be anyone else to carry on the torch. To ask the big questions, to try to understand the universe. Or maybe intelligence is common, but technological civilizations are short-lived. Maybe every species that develops technology ends up destroying itself within a few centuries. Maybe the galaxy has seen thousands or millions of civilizations rise and fall, none lasting long enough to spread to the stars. Maybe we're doomed to repeat that pattern. This is sometimes called the Great Silence. We've been listening for radio signals from other civilizations for decades with programs like SETI, and we've heard nothing, not a whisper. Either we're alone, or everyone else is staying quiet, or they're all gone. But let's be optimistic. Let's imagine humanity survives, thrives, spreads to the stars. In 5 billion years, when the sun begins its transformation into a red giant, humanity will have had time to colonize thousands, maybe millions of worlds. Earth will be remembered as the homeworld, the cradle of humanity, but it won't be home anymore. People, or whatever we've become, will live on countless planets orbiting other stars, in artificial habitats in deep space, maybe even in other galaxies. When the sun becomes a red giant, it will be observed from afar, studied by scientists billions of years more advanced than we are today. They'll watch the sun swell, track its mass loss, observe the formation of the planetary nebula. Maybe they'll even be able to save some artifacts from Earth before it's destroyed, preserved in museums as relics of our species' origin. The destruction of Earth will be mourned, the way we might mourn the loss of a historical building or a piece of art, sad but not catastrophic. Or maybe there will be a project to save Earth. With sufficiently advanced technology, it might be possible to physically move the planet to a safe orbit, using some kind of massive engine or repeated asteroid impacts to gradually nudge Earth outward. This sounds absurd, but it's theoretically possible. Or maybe Earth's fate is seen as natural and right, the way we see the metamorphosis of a caterpillar into a butterfly. Earth served its purpose, it was the cradle of life, and now life has moved on. The planet can return to the cosmos in peace. The sun itself will be studied in incredible detail during its red giant phase. Scientists will want to test their models of stellar evolution against reality. They'll measure the mass loss rate, the surface temperature, the chemical composition of the ejected material. They'll watch the helium flash. If it's somehow observable from outside, they'll track the thermal pulses during the AGB phase. This will be a golden age for stellar astrophysics, a once-in-a-civilization opportunity to observe a star's death up close. And then, when the sun sheds its outer layers and becomes a white dwarf, that too will be studied. White dwarfs are fascinating objects in their own right. They're laboratories for extreme physics, matter at densities and pressures impossible to reproduce on Earth. The sun's white dwarf will slowly cool, its spectrum shifting toward the red over billions of years. Astronomers of the far future will continue to observe it, tracking its cooling, using it as a test bed for theories of degenerate matter and quantum physics. Eventually, trillions of years from now, the sun's white dwarf will be one of countless billions of white dwarfs scattered throughout the galaxy. It will be indistinguishable from any other, a faint, cool ember drifting through the darkness. No one will remember that this particular white dwarf was once the sun, the star that gave rise to Earth, to life, to humanity. It will be anonymous, just another stellar remnant in a galaxy full of them. Unless we leave a marker, maybe some far future descendant of humanity will decide to create a monument, something to mark the location of the solar system, to say, this was where we came from. Maybe they'll place a beacon in orbit around the white dwarf, a structure that broadcasts information about human history, about Earth, about everything we were and everything we became, a cosmic tombstone for our home system. Or maybe not, maybe memory fades, maybe after millions or billions of years. The exact location of Earth is forgotten. Star systems come and go, the galaxy rotates, stars move in their orbits around the galactic center. Without active record keeping, it would be easy to lose track of which star was which. The sun might simply be lost to history, its role in the origin of humanity known in general terms but not specifically. This is not necessarily sad, it's the natural order of things. We don't remember the name of every person who ever lived, even though each of them had a life, dreams, experiences as real and important to them as ours are to us. We don't remember every place that was important to our ancestors. Memory fades. This is the nature of time. and on cosmic timescales, even stars are forgotten. But the effects persist, even if no one remembers the sun specifically, its legacy continues. The carbon and oxygen created in its core, blown into space by the planetary nebula, will mix with the interstellar medium. Some of that material will be incorporated into new stars and planets. Somewhere, billions of years from now, a planet might form containing atoms that were once part of the sun. Life might arise on that planet, intelligent life might eventually evolve. They'll look up at their star, their sun, not knowing that some of the atoms in their bodies, and some of the atoms in their star, originated in our sun billions of years earlier. This is the cosmic cycle, the wheel of stellar death and rebirth that has been turning for most of the universe's history. Stars die, but their material persists, recycled into new stars, new planets, new life. The atoms in your body have been through this cycle multiple times. You are made of star stuff, not metaphorically, but literally. The iron in your blood was forged in a supernova explosion billions of years ago. The calcium in your bones was created in a dying star and scattered across space. You are an assemblage of stellar ashes, temporarily organized into a conscious, thinking being.